Right. So let's recall all the methods you already learned to check convergence of a series. We learned the nth term test. First, we have a special series called P series and the geometry series. Okay, so we know when they're convergent, when they're divergent. Then we have the so-called nth term test, which only used for check the divergence, to prove the divergence of series, because it says that if it's convergent, then nth term approaches 0. Then the next one is the integral test, which also give us the information about the P series. Okay, when it's convergent, when it's divergent. Then after that, we learned comparison test and the limited comparison test. Okay. Then alternating series test. Then ratio test, the row test. That's it. So how do you apply the? So when you see an alternating series, don't try to use alternating series test to prove convergence. Maybe there's maybe that's a quick way to do that, right? Just like what we did for this, for that problem, -1 to the power n over 1 over n squared. So let's see the following problem. Right? This is the natural log of n over 3n plus 1. Okay. So let's take a look at this problem. Okay, first of all, what's natural log of n, right? We look at this term. We look at this, we find out right? If n approaches, yeah, let's look at the limit. The limit of natural log of n over 3n plus 1. The limit is going to be what? It's going to be 1/3. Right now it's going to be 0. So 1/3 is not going to be 0. Just one line. Then you say that the series is divergent by the nth term test, okay, for divergence. The next problem is also, yeah, it's alternating series. Okay, so you get -1 to n. Now this is alternating series. What is the best way to solve this problem? I believe it's convergent, but how do you prove it? And if you want, yeah, this alternate does not mean, I'm trying to tell you, it's not always necessary to use alternating series to prove it's convergent. Okay, it's why it's difficult, because here, if you use alternating series, the Bn is going to be square n over n squared plus 1, right? So corresponding function, you have to prove it's decreasing. The corresponding function will be this. Now you have to prove this decreasing, right? Then you have to find the derivative, okay? So derivative of this function, it works, but it takes a little bit more time. So derivative of square x is going to be this, minus square x times the derivative of x squared plus 1. Okay. So you have to, so let's move 2 square x to the denominator. Okay, so what is left here is only x plus 1. And here you get 2, 2, so 4. Square x times 2x is x, then have x squared. So you get 1 minus 3x squared and 2 square x, x squared plus 1. So clearly this is going to be negative if x is greater than or equal to 1, right? Therefore, this function is decreasing on the interval from 0 to infinity, and then Bn is decreasing. And not only decreasing, you have to prove that it's decreasing to 0. Okay, so limit of n infinity, limit of Bn as n approaches infinity is clearly going to be 0. It's going to be 0. Okay, therefore you can say it's convergent by the alternating series set. So the series is convergent by the alternating series test. So let's look at, it works, right? But that takes too much space, and you have to maybe write on the back side of the of the page. It works. It takes more time. Okay. If something is missing here, and you're not going to get full credits. Okay, you only can prove that it's convergent. There's another way to do is just go back to this problem. Right? So let's go back to this problem. Actually, how do I know this is convergent at the beginning? I look at assuming this is a no negative sign there. Right? It's a square n over n squared plus 1. So it is almost equivalent to the P series. P is 2 minus 1/2 is 3 over 2, which is still larger than 1. Okay. So what they do is just get rid of the absolute very symbol. Okay. This is going to be less than, or it's actually is equal to, but this is less than or equal to square n over n squared, which is 1 over n 3 over 2. Okay. And by the P series test, I know this is convergent. Okay, we know that, okay? By the P series test. Okay. So this is the convergent. Then implies you cannot apply the comparison test directly to the alternating series. Okay, that is one. Now you can conclude that this is convergent. Okay, why you can apply the comparison test? Because this is not, all the terms are non-negative, only under that condition. But if this is convergent, that implies the original series is convergent. Actually, we call it absolute convergent. Okay, so this implies it's convergent. Okay. The next problem, well, such like this one, if it's just n plus 1, then This is still convergent. It is conditionally convergent. It is convergent. It's convergent, but not absolute convergent. How do I see that? Well, I believe that this Vn plus 1 still convergent, decreasing to 0, okay? And by the same argument as above, okay? By the same argument. Okay. You can show that. Just the derivative will be negative, okay? So then that implies this is a convergent. By the alternating series test. Now, whether this is absolute convergent or not. Well, if you look at this, if you look at this, okay, it's going to be divergent. So the reason is I cannot use a comparison test directly, but it's harder to. This is my n. This is almost equal to n. That's going to be n to the 1/2. This is my n. Okay. So use the limited comparison test. You can prove that. Then the limit is 1. Okay. If the limit is 1, then these two series, the convergence are equivalent. They have equivalent convergence. Okay. If one of them is divergent, then the other one is divergent. Okay. So, but this is condivergent. The series of Bn. This is divergent. We know that, right? Okay. By the P series test, if P is P is 1/2. Okay. So this implies is divergent. Okay. By the limited comparison test. If you don't see exponential function or n factorial, don't use the ratio and comparison test, ratio or load test. They're not working. Okay. If you use a ratio test, you're not able to get. You get the limit is going to be 1, but which is useless. Okay. But something like this. Okay. And you have an n factorial. It's a strange exponential function, but that's n to the n. Okay. So I think it's divergent. For this particular problem, I can use a ratio test. I can try use a ratio test. No, I cannot use a ratio test. I cannot use a load test. Why cannot use a ratio test? Even it's n factorial because it's harder to find a limit. You can look, you can try. N plus 1 factor is okay, but the n plus 1 to the n plus 1. Here's n to the n factorial. How do you simplify it? Right? So let's try. So n factor n plus 1 is n plus 1, n to the n plus 1 to the n plus 1. So you cancel n plus 1, you can n plus 1 to the n to the n. It's not too bad. And then you move into this, it's 1 plus 1 of n to the nth power. Are you familiar with this? What is the limit? E, right? It's convergent to E as n goes to infinity. Okay. So the ratio test this time, we're lucky we find the limit. I thought that we cannot, right? So it's going to be E, which is greater than 1. Okay. So that means divergent. By the ratio test. Let's go back to this again. It's n to the nth power n factorial. I think we just need to prove this is not going to be 0 in limit, right? So clearly, it's 1 times 2 times 3 all the way to n. Here's n. Clearly, this is going to be greater than 1. That's much easier way to do. Okay? So the problems have multiple solutions, but some it's easier. Like this one, it's greater than 1. So that implies it's not going to be 0. So therefore, it's divergent. By the Einstein test. Okay. So a problem can be solved in many different ways. And this is the simplest method. It's not a standard method. It's just, it's trying to prove this is again not going to be 1. Again, the limit is not going to be 0. Okay. Yeah, ratio tests, local tests are very useful for power series, okay, to define the radius convergence. Right, so let's take a look at the next problem. But let's look at find the radius convergence and determine the interval of convergence. Okay. I look at this problem. I know it's going to be actually the functions are absolute convergent over the closed interval from -5 to +5. So my answer is, including the endpoints, they're both Both endpoints, the function is absolutely convergent. And outside the interval, it's not. So this defines nice function of the interval. Okay. So how do you do that? Well, you use a ratio test. Okay, so the negative sign would be gone. Don't worry about that. Okay, then let's simplify. So I get this upside down, right? N squared after n. So this one x is left. So I got n over n plus 1 square, 1 over 5. And this is again absolute of x. So the limit is going to be absolute x divided by 5. So clearly, when this is less than 1, okay, the series is absolutely convergent. When, yeah, the series, this series is absolutely convergent. This is absolutely convergent. For absolute x divided by 5 less than 1. Right? But how about at the end point? For this, in this particular case, at both endpoints are absolutely convergent, because at x was absolute x is going to be 1, is going to be 5. Then when you look at the absolute value, you will get 1 over n squared. This is convergent. Okay. That's why it's absolutely convergent at the end point, because it doesn't matter whether x is positive 5 or negative 5, right? And there's a reason there's n squared there. If there's no n squared, be careful. Yeah, it depends on the sign. If it's alternating series, then it's convergent. If it's not, then it's divergent. If the power p is less than 1. Okay? So we don't, yeah. So inside the interval, you can differentiate. Now, you can let the function to be this, right? So you get function over the interval from -5 to +5. Okay. And here x is less than or equal to 5. This can be defined at the end point. All right, so what we can do? We can differentiate. Okay. We can differentiate in the interval. So it's going to be n times n and n minus 1. This holds for x less than 1. Okay, otherwise you cannot differentiate. However, for this new series, f is only defined, f prime can be extended to at one endpoint. It's not defined as an endpoint. So this can be you see the function is defined the closed interval, right? Close the interval. So when you talk about derivative, usually it's for the number on inside interval. But how about at the boundary? At the boundary, we use a left limit. Okay. Yeah. So this f5 is defined. Okay, it's convergent, but f prime and -5 is undefined. Okay. So for the derivative, the power series is only defined from -5 to +5, including 5. Okay, so that's why we put an open set, open interval. Okay. And so f prime 5 use the left-handed limit, okay, to define the derivative, and this is given by this series. Now, if you differentiate further, okay, you will get okay. So maybe we start from 2. Okay, for this one, it's not the power series is not convergent at the 2 endpoints. Okay, so this is convergent if and only if absolute x is less than 1. It doesn't matter what the endpoint is not equal. So when you differentiate the power series, the open interval still there. The function is always absolute convergent at the end, inside the interval, open interval, but it could be divergent at the endpoint. Okay, it's not yeah. So this is a convergent. It is convergent. I mean, the series is convergent if and only if, yeah, it's already, yeah, I already said that. Okay, so it is convergent if and only if absolute x is less than 1. So, but then it will stay there. It's not like the interval convergence shrinking. Okay, the interval convergence is still there. Only, end points now no longer, at the end point no longer differentiable. Okay. Right. I'm not even looking at this. This is not a good example. Right, so my So if we know, okay, here's the question. So let f of x to be where it is. It's gone. Right. So if it's going to be negative n, let me repeat this again, 5 to the n, x to the n. Okay. Find the Taylor series for the function f. Okay. Well, this is a stupid question because here this is a x is less than 5. So the power series on the right-hand side is absolute convergent for x less absolute value of x less than 5. So it's defined function, the function becomes like that. Now, find the Taylor series for this function. According to the definition, your answer should be just itself. Okay? The power, the function f of x is mystery, right? So we can say the first question, there are two questions. First question is, yeah, you can evaluate, you can find a simple expression for fx. Find the Taylor expansion. Okay. Taylor series for the function at x equals 0, at a equals 0. The answer is, by the theorems, this is Taylor series. Okay. Okay. So it is, the answer will be the same. You don't need to do any computation. Right. Yeah. The reason is the coefficient must match with that. Okay. So this is a Taylor series. Okay. Now, can you find the, yeah, what is f right now? In this particular case, I can find f. Okay. fx is going to be, I can put x to the negative x over 5 to the power n. Okay. So this is by the formula, right? It's going to be 1 over 1 minus negative x. So actually it's going to be 5 over 5 plus x. Okay, so given a function x over 1 plus x squared, find the Taylor series or Maclaurin series for f of x. If I say Maclaurin series, I don't need to mention which point because a is going to be 0. Okay, okay, how do you do this? Well, according to the definition, Maclaurin series is going to be this. But if you really want to find the derivative, it's almost impossible to get a general formula. No way you can use it. No way you can find the general formula for the nth order derivative. So complicated. So the best way to do is to use the already known result to find the power series representation for this function. Then that power series representation must be the Maclaurin series. Okay. But it's easier to find the power series representation. Okay. So here's the theorem. If this function is going to be this for x less than r, right? I is positive. Then this Cn is nothing but this, okay? So IE, this is going to be the Maclaurin series. Okay? Right, so that's Maclaurin series. So all I have to do is just find the power series. Okay, you don't need to find the derivative. But I know there are a number of students always trying to find the derivative. That's some formulas I remember. Okay, that's okay. That's a definition from the power series. Maclaurin series. Maclaurin series is defined to be that series whose coefficients is the nth order derivative evaluated at 0 divided by n factorial. But does not mean this. You have to go through that step to get the Maclaurin. If you just find the Maclaurin series, you know, even if you find the derivatives to find the Maclaurin series, then you even don't know whether it's still equal. Okay, convergent to the function. So how do I do that? Well, several steps. Fx is going to be 1 plus x squared, right? Step 1, I'm going to find 1 over 1 plus x. Okay, it is going to be 1 over 1 minus negative x squared. So using the geometric series, I get negative x squared to the power m, as long as this is a less than 1. But this is equivalent to x less than 2. So I got that for x less than 1. All right, then in order to get power series of x over 1 plus x squared, I just needed to multiply each term by x. Right, so I get a power series representation for this function. Okay, then this must be the Maclaurin series. Okay. So this implies is the Maclaurin series. Okay. It's Maclaurin series. But we are using this identity, we can do something else. So we can integrate both sides. I find out this side is going to be natural log 1 plus x squared and divided by 1/2. So it's going to be square root of that. Okay. So other side is going to be entire derivative of that function is 2n plus 2, x2n plus 2, and plus constant. So I can regroup them. It's 2n plus 2. I can start from 1. So n plus 1 is going k. K starts from 1. And then negative k minus 1 is k, 2k x to the power 2k. So fx is 10 to the x. find the Maclaurin series for this function. So in other words, well, if we can find the nth order derivative, that's fine. Okay. So the Maclaurin series is going to be right. So if we are able to find the nth order, I think at this time we can do it directly without any problem. Right? I can do like that. So f prime x is going to be 10 to the x natural 10. F double prime x is going to be 10 to the x natural 10 squared. And so on. Okay. So it's easy to figure out the general formula, then you can get 10 to the 0 natural log 2 to the power k. So the Maclaurin series is going to be n factorial and natural log 2 to the power k and x to the power k. But we don't know this is going to be the equal to the function. Okay? This is the Maclaurin series. Maclaurin series just this. So you still have the question whether this is going to be convergent to the function. Right? Question. Is 10 to the x equal to this? We don't know. This is supposed to be k. Okay. Question that they're equal now. Then you have to go through all the procedures. You have to prove that y equal. So if you just find the Maclaurin series, just find. If you want to find the Maclaurin series, just find partial derivatives. Then you get a series. But if you want to know more, if you want to know more about that, then you have to prove they're equal. Okay, for x less than 1 number, for x less than some number. So we even don't know the convergence radius. Okay. I think this is true for any x. All right. So what is another way to prove to get the Maclaurin series? Not only that, we also know whether the Maclaurin series is convergent to the function n to the x. So here's the best way to. So we know, again, we go back. E to the x is going to be this. Right, we know. Recall. But E is not going to be 10. But you can modify it. Okay? 10 to the x is going to be natural log of e to the natural log of 10 to the x. Which is e to the x natural log of 10. Okay, according to the formula, above the formula. Okay, you're done. So we not only get Maclaurin series, we also prove that the function is equal to Maclaurin series. Okay, that's a good part. So manipulate the given function and using the well-known formula, you can get the Taylor series or Maclaurin series for general function. Find the Taylor series for the function right? Can you do this? Find the Taylor series for this function at point A. Okay. First of all, we record the formula, right? This is a Taylor series at its origin. And this is a x is less than equal to 1. Don't be misleading. Okay. So we are looking for, we want to express it in the form, in this form, right? And the x minus 2 should be less than some number. I think less than 1. Yeah, the reason is here's 1, here's 2. This is the functions undefined. So you have to look at the interval. Okay, that's right. So it's 1. Right? You cannot. Yeah, you shouldn't find the derivatives of the function to solve the problem. So what you're going to do is you let u to be x minus 2, and x is going to be a u plus 2. So you plug. So you will get 1 minus 2, negative 1 minus u. We're almost done. It's negative 1 plus u. right? It's going to be 1 minus negative u. Then you apply above formula. Okay. Finally, we get the answer. That is going to be x minus 2 to the power x. Great. Okay. So let me ask you to do another one. Find as a characteristic for the function f of x, natural log of x at a equals e. How about that? All right, so we record the formula, right? Natural log. If you don't, you should memorize all the formulas on the table, right? If you don't remember the 1 over 1 minus x, and you can integrate on both sides, okay? So this is there was a negative sign in front of that, right? So we have this is section last. All right, so this is on page 808. Okay, natural log. Where's natural log? It's natural log of 1. That's formula is 1 minus 1 plus x. It's okay. So then you have a alternating series. Okay, and start from 1. So this is what we know. All right. Then how can I use that? This is for x less than 1. When x equals -1, it's going to be 0, so it's not. Okay. Natural log of x is defined at e. So what we can do is let u to be x minus e, right? So then x is u plus e. So let's put back. So f of x is going to be natural log of u plus e. How can I express in the form 1 plus x? You take e out, right? Okay. Then you separate that. Natural log of e plus natural log of 1 plus u of e. Natural log of e is 1. Then it's plus x, so that's why n start from 1, negative n minus 1, right? Yeah. N over n and x, u over e to the power n. So that's it. Then you write it again. And you have n times e to the power n, u to the n. So u to the n is nothing but x minus e to the power n. Okay, so that's what I got. Okay, find the power series representation for the function f of x equals e to the x minus 1 minus x divided by x squared. Whoa. Okay, no, I'm not going to divide by. All right, so this is just a little bit, I think it's a trivial problem because you know e to the x, it's going to be start from 0, n factorial x to the n, minus 1 minus x, right? So if you write down the first two terms, you get 1 plus x. And plus when x equals 2, n factorial x to the n, minus 1 minus x, so that be cancelled out. Right, start from 2. And you have to say when it's convergent, so x is convergent for any x. Now, the next question is, find the Taylor series for the function f of x equals x minus 1 to the fourth power at a equals 0. Yeah, how do you do this problem? Okay, so this one, a polynomial. Remember, for a polynomial, right, itself, it's already a Maclaurin series. And you don't need to do anything. But you have to express as a polynomial in the general form. So what you get is f of x is going to be, how do you multiply this out? Well, you have to do like step by step, maybe. Square, right? So I get x squared plus 2x plus 1, then square. Okay, you know how to square the three terms, x to the fourth, 4x squared plus 1, and then twice 2 to 4x cubed, and 2 to 4x, and 2x squared. Okay, so if I, the constant terms first. So you get 1, where's the 4x, and x squared, and the 4x cubed plus x to the 4. Yeah, this is a polynomial. Great. Okay. So this is it is a power series representation for the polynomial. The polynomial is a trivial one, right? Here's another question. Here's another question. Find the Taylor series for this function x plus 1 to the fourth power at a equals at let's see, at 1. Okay, can you do that? Okay, it's the same idea. So u equals x minus 1, right? Then x is going to be u plus 1. So f of x, let's go back to the original one, right? It's x minus 1 cubed at fourth power, right? So the fourth power, you get x is u plus 1 and plus 1 to the fourth power. Right? So it's going to be u plus 2 to the fourth power. Then you multiply this out. It's u to the fourth power. And I'm trying to get all the coefficients. Okay, it's a little bit difficult right now. So let's step by step. Does not take too much time. So this square plus 4u plus 4, then square. Okay. So I get u to the fourth power. You multiply this out, and 16u squared and 16. That's the first part. And twice of that is 80u cubed. Twice of this, 32u plus 80u squared. Okay. So write down that it is 16 plus 32 plus 8 square, so it's 24 square, and then 8 u cubed plus u to the fourth power. So now you can express it in the form x minus 1, right? Use x minus 1. And 24x minus 1 square, 8x minus 1 cubed, plus x minus 1 to the fourth power. So as long as you can express in this form, then this is a Taylor series. Not only that, they're equal. Okay? Nothing about the convergence because there's only finite many terms there. All right, so that's it. We've